Hello, everyone. So we're going to continue our discussion of the bio-inspired materials. We're going to look at the building block of the brick and mortar structure. So the building block is very much similar to what you saw in the case of carbon nanotube structures. Actually, the initial concept is exactly the same. You have two tablets or bricks, 1 and 2, and they have an interface between, they have an interleave between them. They have a layering between them that is carrying load from one to the other. The main difference between this and what we studied in carbon nanotube structures is that here we're limiting our study to 2D structures. So imagine that the real structure is something like this. So basically two bricks that are one on top of the other. But here I'm going to assume that the thickness of each brick is 1. So, so basically this investigation is per unit thickness. Therefore, if the stress at this far end, axial stress, is sigma 0, the force applied will be sigma 0 times B times 1. 1 is the thickness of the unit thickness that I mentioned to you earlier. Now, this is not drawn to scale. In reality, B is going to be much, much smaller than L. So this more or less behaves like a 1D material. So then, because of equilibrium, there will be a force equal to sigma 0 B on the other end as well. Now, there's a mistake in my notes. Please clarify this. This value is gamma of E, not gamma of F. So now, so I told you the boundary conditions. The dimensions are given here, including the thickness of the mortar, the length of the mortar, the width of the bricks. And here's traction free. There's no force or stress here as well. Now, as far as the material behavior, the mortar, this region in the middle, we are going to assume that behaves like this. Tau, shear stress, as a function of gamma, initially goes up linearly. Then when a yield stress, tau F, is reached, it deforms plastically, but without any increase in stress. So this is a type of behavior that we call elastic, perfectly plastic. So EPP. So basically, we can simply say EPP, elastic, perfectly plastic. When the shear stress strain reaches this value, the mortar breaks. Now, because we're modeling biological materials, we're going to assume that the bricks act linear elastically until failure. So if I want to briefly draw the stress strain curve of the bricks, sigma versus axial strain is like that. It breaks at a normal stress that I call sigma F. So basically, we have the material properties, we have the boundary conditions, we have the dimensions. So we have everything we need to calculate the displacements of each brick, the shear strain in each brick, in the mortar, and all that. So let's start to do this. Now, the first thing I want to do is understand our displacement compatibility equation. So if you look at this guy, I told you it's not drawn to scale. B is actually much smaller than L. So if I want to draw it to scale, perhaps something like this would do it. So 1 and 2. 1 and 2. This is before any loading applied. And when the load is applied, so what's going to happen? Well, this far right will move to the right by some amount. Every point before this to the left will also move slightly to the right, but by a lesser amount, because some of the displacement is resisted by this bottom brick through this interface region, through this mortar region. So imagine I'm looking at an arbitrary point that in 1 and 2, which is located at x. Point 1 moves by u1x, which I am going to show you u1x by this amount. This is how much this point moved to the right. Point 2, which was in tablet 2, will move by a slightly lesser amount, u2, which is a function of x. So now, this line that initially was vertical like that, now it's at a different angle. And when it's at a different angle, it means here we have a shear strain. This is the shear strain that is in the mortar, that's in this region. So the shear strain is this angle in radians, which means this angle is basically this divided by that. This length divided by this length. That is u1 minus u2 divided by h. All of them is a function of x. So this is one of our first compatibility equations that we're driving here. So now I move forward. You remember I told you we're considering both elastic and plastic behavior of the mortar. Let's first look at the elastic behavior. Assume that at every point in this sky, the basically the shear stress in the mortar remains less than tau f. No plasticity yet. So in that regime, gamma and tau are related to each other. So if I know u1 and u2, based on the equation that we derived in the previous page, I can calculate shear strain, gamma. I can multiply it by g. That gives me my tau. Okay? Now, let's look at the tablets as well. One tablet at a time. So imagine I look at a piece of tablet that initially has length dx. Okay, it spans from x here to x plus dx. Now, this point will move by u1 of x, which is shown here. But the right side will move by u1 of x plus dx, because u is the function that takes the initial location of the point and gives you the amount that the point has moved. So now, if this is dx, the new length of the segment is dx prime. Right away, you can see that dx prime plus u1 has to be dx plus u1 x plus dx, or equivalent to that is this equation here. I can rearrange this equation to get this. And the reason I do that is primarily because I want to get this term out. This is new length minus the initial length divided by the initial length. That's the definition of a strain. So basically, this is strain in tablet 1. which is the same as du dx, because this is this. Now, from material property, we know that the strain, axial strain, is the ratio of stress, normal stress, divided by elastic modulus. So this is the elastic modulus of the bricks.